Welcome to this problem walkthrough. In this session, we'll be tackling problem number 1445, titled Apples and Oranges. Get ready to explore the intuition, approaches, and solutions to this interesting challenge. Let's dive in. In this problem, you are tasked with finding the minimum cost of buying one apple and one orange under specific conditions. You are given two arrays, apples and oranges, where each element in these arrays represents the price of an apple or an orange at a specific store. The key requirement is that the apple and the orange must come from different stores, meaning you cannot select both items from the same store. If it is impossible to satisfy this condition, you need to return -1. For the input format, the apples array has a length between 1 and 10,000, and each price is a positive integer between 1 and 1 million. Similarly, the oranges array has the same constraints. The output should be a single integer representing the minimum cost or -1 if no valid pairing can be made. Let's look at the first example to understand this better. Here, the input arrays are apples equals 4, 2, 3, and oranges equals 5, 1, 6. To minimize the cost, we need to choose an apple and an orange from different stores. A valid combination would be selecting the apple from the second store, which costs 2, and the orange from the second store, which costs 1. However, since they need to come from different stores, we select the apple from store 2 and the orange from store 3 instead. This results in a total cost of 2 plus 1 is equal to 3. Thus, the output for this example is 3. In the second example, the input arrays are apples equals 7, 8, and oranges equals 3, 2. To find the minimum cost, we can choose the apple from the first store, priced at 7, and the orange from the second store, priced at 2. This combination results in a total cost of 7 plus 2 is equal to 9. Therefore, the output for this example is 9. Remember, the condition that the apple and orange must come from different stores is still being upheld. In the third example, the input arrays are apples equals 1 and oranges equals 1. Here, there is only one store available. Since the problem requires the apple and the orange to come from different stores, it is impossible to make a valid selection. As a result, the output is -1. Additionally, the constraints emphasize that you should handle edge cases efficiently, such as when one of the arrays has only one element or when the arrays are large. Ensure your solution works for any valid input, and note that all prices are positive integers, so negative or zero values do not need to be considered. To tackle this problem, the most straightforward approach is to use brute force. The intuition here is simple. We iterate through every possible pair of an apple and an orange, and for each pair, we calculate the total cost. If the apple and orange come from different stores, we check whether the total cost is the lowest we've encountered so far and update our minimum cost accordingly. This can be implemented using two nested loops. The outer loop goes through the apples array, while the inner loop iterates through the oranges array. For each pair, we verify that the indices of the apple and orange are different, ensuring they are from separate stores. While this approach is easy to understand and implement, it has significant drawbacks. Specifically, its time complexity is O and *m, where n and m are the lengths of the two arrays. This means that as the number of apples and oranges grows, the runtime increases dramatically. Additionally, since no extra memory is required, the space complexity remains constant at O(1). However, for larger input sizes, this brute force approach is inefficient and impractical, prompting us to consider more optimized solutions. To improve efficiency, we can adopt an optimized approach that avoids iterating over all combinations. Instead of checking every pair, the goal is to focus on finding the minimum apple price from one store and the minimum orange price from a different store. This drastically reduces the number of comparisons. First, we identify the minimum price and its index in the apples array, which we call min_apple and min_apple_idx. Similarly, we find the minimum price and index in the oranges array, denoted as min_orange and min_orange_idx. If the indices of these minimum values are different, it means the apple and orange are from separate stores, and we can directly return the sum of their prices. However, if the indices are the same, we need to ensure the apple and orange come from different stores. To do this, we find the second minimum price in either the apples or oranges array, depending on the situation. This guarantees that we meet the store constraint while still minimizing the cost. The time complexity of this approach is O(n plus m), because we only make one or two passes through each array to find the minimum and second minimum values. The space complexity remains O(1), since no additional data structures are required. This makes the solution both efficient and lightweight. This optimized approach offers significant advantages over brute force, but it's not without its trade-offs. While it is much faster, especially for large input sizes, it requires careful handling of edge cases, such as when one or both arrays have only a single element. Despite these challenges, we have chosen the optimized approach as our strategy because it balances clarity and performance exceptionally well. The brute force approach, while simple, is computationally expensive, making it unsuitable for the problem's constraints. By leveraging the concept of the minimum and second minimum values, we ensure correctness while achieving efficiency. The key observation that underpins this strategy is recognizing that the problem revolves around minimizing the cost while ensuring the apple and orange come from different stores. Using this insight, we can avoid evaluating every pair explicitly and instead focus on a few critical values. This insight not only reduces computational workload but also makes the solution more elegant and scalable. When considering alternative approaches, we find that none are as efficient or suitable as the optimized strategy we've chosen. For example, a sorting-based approach, where we sort both arrays and then find valid pairs, could work. However, sorting introduces an overhead of O(n log n plus m log m, which makes it less efficient than our O(n plus m) solution. Similarly, a greedy pairing strategy, where we simply pick the smallest values without considering their indices, fails to meet the store constraint. This results in incorrect solutions since it doesn't ensure that the apple and orange come from different stores. Our chosen approach stands out because it achieves optimal time and space complexity, addresses edge cases effectively, and is straightforward to implement. By focusing on the minimum and second minimum values, we maintain accuracy while avoiding unnecessary computations, making it the best solution for this problem. In this problem, we need to find the minimum total cost of purchasing one apple and one orange, making sure that they are bought from different stores. Each store has its own price for apples and oranges, which are provided in two separate arrays. To start with, we can solve this problem using a brute force approach. The intuition behind this approach is simple. We calculate the cost for every possible pair of apple and orange prices from different stores, and then keep track of the smallest cost among all valid combinations. To set this up, we first represent the prices using two arrays, where apples, I, gives the price of an apple at store I, and oranges, J, gives the price of an orange at store J. Both arrays are of the same size, representing the number of stores. We then initialize a variable, min_cost, and set it to infinity. This variable will store the smallest total cost that we find as we iterate through the combinations. To compute the minimum cost, we iterate over all possible combinations of stores. For each store I that sells apples, we look at every store J that sells oranges. For a pair to be valid, the condition I equals J must be satisfied, ensuring the apple and orange are purchased from different stores. If this condition is met, we calculate the total cost for that pair as apples, I, plus oranges, J. If this total cost is smaller than the current value of min_cost, we update min_cost to this new value. After checking all valid pairs, the value stored in min_cost will be our result, representing the minimum total cost of buying one apple and one orange from different stores. This approach, while straightforward, involves examining every possible pair of stores, which can be computationally expensive for large input sizes. One of the key insights of this problem is that the constraint I equals J ensures we are always selecting an apple and an orange from different stores, which is fundamental to the problem. However, the brute force approach, while simple to implement, has a time complexity of O(n²), due to the nested loops required to evaluate all combinations. This presents an opportunity for optimization. By pre-computing certain values, we can reduce the time complexity to O(n). The optimized approach relies on calculating, for each store, the minimum orange price available across all other stores. This allows us to avoid iterating through all combinations, as we can directly compute the minimum cost for each apple price by adding it to the pre-computed minimum orange price from other stores. This significantly reduces the number of operations needed to find the solution. To implement the optimized approach, we start by pre-computing the minimum orange price across all stores. This can be done in a single pass through the oranges array. Once we have this value, we iterate through each store I to evaluate the cost of purchasing an apple from that store. For each apple price at store I, we check if it can form a smaller total cost with the pre-computed minimum orange price from other stores. If it does, we update the min_cost variable to reflect this new minimum. After iterating through all the stores, the final value in min_cost will represent the smallest total cost of buying one apple and one orange while adhering to the problem's constraint. To efficiently solve this problem, we primarily use arrays and a few variables. The arrays store the prices of apples and oranges, while variables like min_cost and min_orange are used to track the lowest total cost and the minimum orange price, respectively. It's also important to consider edge cases. For instance, if there is only one store, it's impossible to satisfy the constraint of buying from different stores, so the algorithm should return an error or a sentinel value. If prices are negative, perhaps due to discounts, the algorithm still functions correctly, as it simply finds the smallest sum. For very large inputs, the optimized approach helps ensure that the algorithm remains efficient, running in O(n) time. Finally, let's analyze the complexity of our approaches. The brute force solution has a time complexity of O(n²), because it evaluates all possible combinations of apple and orange prices from different stores. In contrast, the optimized approach reduces this to O(n) by leveraging pre-computed values to avoid redundant calculations. The space complexity for both approaches remains O(1), as we only use a few variables in addition to the input arrays. This makes the optimized approach not only faster but also space efficient, making it suitable for handling large inputs effectively. This code solves the problem of finding the minimum cost of buying one apple and one orange from different stores. The function mincost takes two lists as inputs: apples for the cost of apples in different stores and oranges for the cost of oranges in different stores. First, we initialize min_cost to infinity, which will keep track of the minimum cost found so far. We then iterate over all combinations of stores using two nested loops. The outer loop iterates through the apples list, representing the costs of apples in each store, and the inner loop iterates through the oranges list, representing the costs of oranges in each store. Within the nested loops, we ensure that the apple and orange are bought from different stores by checking if the indices I and j are not equal. If the condition is satisfied, we calculate the total cost of buying an apple from store I and an orange from store j. We then update min_cost if the calculated cost is less than the current min_cost. Finally, after all combinations have been checked, we return the min_cost, which now holds the minimum possible cost of buying one apple and one orange from different stores. This approach ensures that all valid combinations are considered, and the solution is both correct and efficient for small to medium input sizes. This is the Java implementation of the apples and oranges problem, LeetCode number 1445. The logic mirrors the Python implementation, iterating through all possible combinations of apple and orange prices while ensuring they are purchased from different stores. Key differences include the use of Java's int type for arrays and the math.min method for calculating the minimum cost. This implementation maintains the same time complexity of O(n²), where n is the length of the input arrays. In this problem, we aim to find the minimum cost to buy one apple and one orange, ensuring they are selected from different stores. We are provided with two lists, apples and oranges, where each element represents the price of apples or oranges at a particular store. To solve this, we use a nested loop approach. First, we initialize min_cost to infinity to keep track of the smallest total cost. Then, we iterate over all the possible stores for apples using the outer loop, represented by the index I. For each store I, we check prices in all other stores for oranges using the inner loop, represented by the index j. However, if I and j are equal, meaning the apple and orange are from the same store, we skip that combination. For example, let's consider the input lists: apples equals 3, 5, 1, and oranges equals 2, 8, 4. In the first outer loop iteration, we focus on the apple at store 0, which costs 3. In the inner loop, we skip store 0 for oranges since I equals j. Moving forward, we start evaluating other combinations to find the total cost. Now, with the apple price at store 0 being 3, we examine oranges from other stores. When j equals 1, the orange price at store 1 is 8, giving a total cost of 3 plus 8, which equals 11. We update min_cost to 11 since it's smaller than the current value of infinity. Next, with j equals 2, the orange price at store 2 is 4, resulting in a total cost of 3 plus 4 is equal to 7. This is now the smallest total cost, so we update min_cost to 7. After completing the inner loop for store 0's apple, we move to the apple at store 1, which costs 5. Here, when j equals 0, the orange costs 2, making the total cost 5 plus 2 is equal to 7. However, since this matches the current min_cost, no update is made. For j equals 2, the orange price is 4, giving a total cost of 5 plus 4 is equal to 9, which is greater than 7, so min_cost remains unchanged. At this point, we have evaluated some valid combinations, but we still need to check the apple from store 2 to ensure all possibilities are considered. With the apple price at store 2 being 1, we proceed to the inner loop to calculate costs with oranges from other stores. For j equals 0, the orange price is 2, resulting in a total cost of 1 plus 2 is equal to 3. This is smaller than the current min_cost of 7, so we update min_cost to 3. Next, for j equals 1, the orange price is 8, giving a total cost of 1 plus 8 is equal to 9, which does not affect the minimum cost. For j equals 2, we skip the combination since I equals j. Having completed all iterations, the final result for this example is min_cost equals 3. Let's now consider another example input, apples equals 10, 15, and oranges equals 25. We use the same approach, starting with initialization and iterating through all valid combinations to find the minimum cost. In this example, we initialize min_cost to infinity. Starting with the apple price at store 0, which is 10, we skip the orange at store 0 due to I equals j. For j equals 1, the orange price is 5, resulting in a total cost of 10 plus 5 is equal to 15. We update min_cost to 15 since it's smaller than infinity. Next, we examine the apple price at store 1, which is 15. For j equals 0, the orange price is 20, giving a total cost of 15 plus 20 is equal to 35. This value does not affect min_cost since it's greater than 15. For j equals 1, we skip the combination due to I equals j. After evaluating all combinations, the final result for this example is min_cost equals 15. Now, let's consider one final example, apples equals 7, 3, 8, and oranges equals 6, 10, 4. In this last example, we use the same method of iterating through all valid pairs of apple and orange stores. By carefully evaluating each combination, we find that the minimum cost is achieved by selecting the apple from store 1, which costs 3, and the orange from store 2, which costs 4. The total cost is 3 plus 4 is equal to 7. To summarize the approach, we iterate over all combinations of apple and orange stores, ensuring that apples and oranges are selected from different stores. We calculate the total cost for each valid combination and track the smallest cost using the min function. The nested loop structure ensures that all pairs are evaluated, resulting in a time complexity of n squared, where n is the length of the input lists. This method guarantees the correct result while being efficient for small to moderate input sizes. In this solution, we calculate the minimum total cost of buying one apple and one orange from different stores. To achieve this, we iterate over two lists, apples and oranges. Let the lengths of these lists be n and m respectively. The outer loop runs n times, as it goes through each element of the apples list. For each iteration of the outer loop, the inner loop runs m times, iterating through all elements of the oranges list. Within these loops, the condition I equals j is checked to ensure we consider only pairs from different stores, and this check is performed in constant time, O1. Additionally, we use the min function to update the minimum cost, which also operates in constant time. Since the nested loops result in n*m iterations and each iteration involves constant time operations, the overall time complexity of this solution is n*m. If n and m are approximately equal, the time complexity simplifies further to n squared. Now, let's analyze the space complexity of the solution. The input lists, apples and oranges, are passed as arguments, so no additional memory is used to store them. The algorithm utilizes one auxiliary variable, min_cost, to keep track of the minimum cost calculated so far, which requires only O1 space. Additionally, the solution does not employ any extra data structures such as arrays, hash maps, or recursion stacks, keeping the memory usage minimal. As a result, the overall space complexity is O1. Furthermore, because the algorithm evaluates all possible pairs of stores I, j, in the same way regardless of the input values, the time complexity remains consistent in all cases: best, average, and worst. This means the time complexity is always O(n*(m). The current solution is a brute force approach that systematically evaluates all possible pairs of stores I, j, with the condition I equals j. While this ensures correctness, it is not efficient for larger input sizes due to the O(n*(m) time complexity. This inefficiency arises from the nested loops that compute the result by directly checking all combinations of apples and oranges. However, a more optimized approach could be designed. For example, we could pre-compute the smallest and second smallest costs in the apples and oranges lists beforehand. By doing so, we could reduce the time complexity to O(n+m), since the nested loops would no longer be necessary. This optimization would significantly improve the algorithm's performance on large inputs. To mathematically justify the time complexity, we observe that the outer loop runs n times, and for each iteration of the outer loop, the inner loop executes m times. Within these loops, only constant time operations are performed, such as checking the condition I equals j and updating the minimum cost. As a result, the total number of operations is directly proportional to n*(m), leading to a time complexity of O(n*(m). On the other hand, the space complexity remains constant because the algorithm uses only a fixed amount of memory, irrespective of the input size. This fixed memory usage, consisting primarily of the min_cost variable, ensures an overall space complexity of O1. When solving problems like these, there are a few common mistakes to watch out for. First, not properly accounting for constraints and edge cases can lead to serious issues. For example, if you're working with combinations of items from two lists, you may encounter cases where one or both lists are empty. Failing to handle these scenarios can easily result in runtime errors. Always take the time to validate your inputs and ensure they meet the constraints given in the problem. Another mistake is relying on brute force solutions for large inputs. While brute force might be simple to write, it often leads to time limit exceeded errors when the input size grows. For instance, iterating through all pairs of items in two lists with sizes n and m gives you a time complexity of O(n*(m), which becomes impractical when n or m exceeds 10,000. Additionally, overlooking sorted data can be costly. If the input lists are already sorted, you can often leverage techniques like binary search or two-pointers to significantly improve efficiency. Finally, failing to handle duplicates correctly is a frequent issue. Some problems require unique combinations, while others allow duplicates. Misinterpreting these requirements can lead to incorrect results, so always read the problem statement carefully to understand how duplicates should be managed. Another common mistake is making assumptions about data types or ranges. For instance, assuming all numbers are positive or within a specific range can lead to bugs when encountering negative numbers, zeros, or maximum values allowed by the problem's constraints. Testing these edge cases is critical to ensure your solution is robust. Now, in an interview setting, optimization plays a major role. Interviewers might ask you to start with a brute force solution but will expect you to optimize it. Be ready to discuss the trade-offs between time and space complexity as you move toward a more efficient approach. Also, be sure to communicate edge cases during your explanation. Acknowledging potential pitfalls, like empty inputs or duplicate handling, demonstrates that you're thorough and attentive to detail. Recognizing problem patterns is another key skill. Problems involving lists or combinations often benefit from techniques like sliding windows, two-pointers, or hash maps. Identifying these patterns early can save significant time. And even if you can't immediately optimize your solution, clearly explaining why a brute force approach is inefficient and identifying its bottlenecks shows strong problem-solving skills. To further enhance your understanding, it's helpful to look at related problems. For example, LeetCode 1-2-sum focuses on finding two numbers that add up to a target value. It's often solved efficiently using a hash map. Another example is LeetCode 15-3-sum, which requires finding triplets that sum to 0. This type of problem highlights the utility of sorting and two-pointer techniques. Extending this idea, LeetCode 18, for sum, builds upon 3sum by increasing the number of elements to 4, emphasizing the need for optimization and careful handling of edge cases. Finally, LeetCode 121, best time to buy and sell stock, is a single-pass problem that showcases how to traverse an array efficiently to find the optimal solution. Exploring these problems can help you recognize patterns and approaches that are applicable to a wide range of scenarios. Now, let's discuss some alternative approaches and the trade-offs they involve. A common method is the hash map approach, where you store values from one list in a hash map and check for matches in the other list. This typically reduces the time complexity to O, n plus m, but it does require additional space. If the input lists are sorted, the sorting and two-pointer technique is another efficient option. By iterating over both lists simultaneously with two pointers, you achieve O, n plus m, time complexity while avoiding extra space. However, this approach depends on the data being sorted. Another technique for sorted inputs is binary search, where you iterate through one list while using binary search in the other. This results in a time complexity of O, n asterisk log m, which can be effective in certain scenarios, though it's usually less efficient than the two-pointer method for fully traversing both lists. Finally, for some variations of the problem, divide and conquer can be a powerful approach. By breaking the problem into smaller subproblems and solving them recursively, you might uncover elegant solutions, though this often comes at the cost of increased implementation complexity. Each of these approaches has its strengths and weaknesses, so understanding the trade-offs is key to selecting the right one for your specific problem. That's a wrap. We've covered the problem, explored the approaches, and highlighted the key takeaways. Remember to keep practicing and applying these techniques in different problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!